All right. So tonight we'll be talking about math. If you have your speaker on, just mute that. So we'll be talking about math, which can be a scary topic. So we're going to try and have as many demos in the class as possible, so you can actually get some hands-on experience rather than just looking at things. We don't quite have time for the pre-class discussion because it's during class. So I'm going to review a couple of comments about the presentations that I observed last week. So you can pull those up. Let's see. So these are minor comments that I didn't want to like distract the presenter at the time. So I just wrote down my comments and then we'll review them. If I used your data set, it wasn't a commentary on you or your presentation so much as like the general theme that I was observing. So don't get offended. So I'm going to use a CSV that was used a couple people, and then it's this. Let's make this a little bit bigger. Right, so the shape of the data frame, right? 185 rows, 12 columns, and so one little comment that's just sort of like a presentation issue is if you just type DF and like get the whole data frame back, there's a lot of content on the screen, right? And like scrolling through this, all 900 rows can be sort of like tedious, right? And like typically doesn't actually add a ton of value. And so the other alternative that I saw a few people use, and this has also been present works, is just saying print DF. I'm not sure what the motive is on that. I can speculate that it makes things slightly better than using the stylistic sort of printing that pandas will do by default, in that it prints columns that don't fit on the screen to like below the first screen, and that actually makes it also confusing. So like to me, that is not a good solution either. It's just hard to read and a lot to scroll through. So what I advocate when I'm looking at a data frame is to look at the head command. And so it provides you only a little bit of the data, which you can adjust if you type in, so like, I don't know if this is. Yeah, so you can change how many rows you see, and that can be sort of useful. And then there's also the tail command, which shows you the bottom of the data frame. So it's just a reminder, if you don't remember, those are commands that make viewing the data frame easier. John?
I think it's an interesting problem where I would do that and it would just print it regularly. It wouldn't make it like look nice or anything.
Okay. Can you reproduce that, or is it?
I can. We'll run through it.
All right. Yeah, I'd like to see that. So there are issues that you guys will bring up in class that I can solve, and some problems that I cannot solve. I won't know this until you present. So like, kind of was talking to me before class with a Docker issue. I can try and troubleshoot, but there's like, I don't have all the answers. So you're welcome to ask me about IT support questions, and I may or may not have the answer. All right. So another trick that we have up our sleeve, besides just looking at the top or bottom of the data frame, is this key command. And I saw one person use that. I was pretty impressed. Basically, what that does is transpose the output. So transpose means convert all the rows to columns and the columns to rows. So basically, take your data frame, rotate 90 degrees. Why would that be useful? And the answer is, if I only display the first few rows, which in this case are displayed as columns, and I have like say hundreds of columns, which are now rows, this display can be sometimes easier depending on the shape of your data frame. So I use it a lot. If sometimes the CSV will have like huge long header strings, and that can get really annoying to try and read in the standard presentation format. And so if you transpose the output, it makes it a lot easier to read. So just a convenience factor again. All right, so this is, so moving on. Does anyone have any questions on presentation? Those are pretty superficial questions. So the next point that I sort of observed was when we load in data and it contains a bunch of nans, sort of like, empty values, the first sort of reaction is, well, we'll just drop all that data, right? Like it's noisy, I don't want to clean it, we'll just drop it. And that may be valid if you only have a few instances of the nan, but if you have a lot, that can actually lose a significant portion of your data. All right, so I load up this Excel file, and then I have 8,800 rows of data, and the number of non-zero entries in that, so the number of nans is 0. So we have no empty values, right? Good to go. Well, so actually, this is where head comes into pretty good use. You'll notice that there are some entries here that have this dash, right? Which the CSV editors, the people who made the Excel spreadsheet, sorry, said to themselves, we'll just put in a little placeholder, and that'll be the empty value. So the right thing to do, right? This is like an opinion, but the right thing in my case would be to replace the dash there notation with an actual nan entry, right? So that we can really clarify it is a placeholder for an empty variable. Now we can go back and count how many of those nans have we introduced, right? We've added nans, and so how many? So it's 10,000. It sounds like a lot. But you have to remember the original shape of the data frame is pretty big. There's 97,000 cells in the data frame. So 10%, like empty values, it's not actually that bad. Right? So percent seems reasonable. The problem is when we have some number of nans and we say, well, we're just going to drop every row that has an empty variable in it, we'll just throw that out. That'll make the job way easier, right? The problem with that is when we drop every row that has a nan in it, we drop more than half the rows. So before we had 8,800, after we drop every row, there's 3,800. So that's a pretty significant loss of data. And the problem is these nans probably are not uniformly distributed through our data. So we, like, let's see if we can pick out any sort of like obvious things, like if there's a disposition that's more likely for checked bags, right? And we drop all the rows with nans in it, now we're introducing some bias into what our expected results are going to be. So either go back, chase the data owner and ask what's going on, or to like try to figure out, like, am I introducing some bias into the data by doing this cleaning or not? So I think that's like a tricky problem to be solving in this class. I just wanted to raise it as an issue so that when you go off, to your real job and you remove all the nans, and you lose more than half your data, that'll be a bit of an issue. Question: nans and cleaning is a tough job. So does anyone have any questions on that section? Ken.
Well, one thing I did was I had quite a few columns that had a lot of nans, and when I did the missing values test and was missing
yep.
that showed me which columns had the nans in it, and I could drop those columns rather than
So I would say that if the columns and rows are sort of like two different stories, right? Like I think of like a row as like an event or some person or something on, whereas a column is like a feature of the data. So I would say dropping a column might be reasonable if you know that none of your analysis ever depends on that. But yeah, whether to drop an entire column or row is an important choice. All right, so, and this is another sort of like pro tip for presentations. When you have a bar chart, the sort of like default method of plotting some data is sort of just like the order in which it appears in Python. Like Python doesn't know any better. It looks pretty nice, right? It's got some colors, got some stuff going on, like there's some stories we can tell. But we might want to make it easier on our audience by ordering the data, right? So it makes comparison way easier. And so like if you have a pretty complicated bar chart where the order of the variables isn't necessarily in some order, like if your bar chart's Monday, Tuesday, Wednesday, Thursday, Friday, there's clearly an order that those should be preserved there. But you can also sort of sort by the size of your bar, in that case making the comparison between data points much easier. So just for comparison, this is exactly the same data, and there's no loss of information in the sense of E is still the lowest value and D is the highest. But once I've ordered that set of values, it's sort of like the ranking becomes clear. Again, not required, just makes it easier for your audience to get the message you're trying to convey. And with the caveat that hopefully the actual variable order shouldn't matter if we do this ordering. And then I think the last sort of comment that I had, this is interesting to me because I had the hardest time trying to explain when to use normalization and when not to. So I still don't have like a super solid story, but I can usually detect when someone should be normalizing their data. So an example, this is going back to the DHS data for TSA data, and this showed up in quite a few people's presentations. So again, I just have all this data, and I want to know like how many times do the various airports show up in that list, right? And that's a very like straightforward question. Like I look at value counts. So this is how many times JFK showed up, 644 rows, pretty straightforward. And I'm only looking at the top 20. So I'm applying that head trick again, so I don't get the full list back. So no big deal there, right? And so you could say, well, Baltimore is way down at the bottom of this list, and JFK is way high, right? Like lots of seizures at JFK, right? Is that really the case, right? And the question comes down to how many people did JFK process through their airport compared to how many people got processed through BWI, right? It's what this list is telling you is really that JFK is popular, right? More popular than BWI. But if you wanted to know, like, is JFK an outlier, right? Is it processing like so many people that even though it has a higher number of TSA claims, it's lower compared to the percentage you'd see from BWI. So it's like, in this case, it would have been useful to normalize the sort of seizures from TSA by the number of people processed at the airport. So that's, and then there's sort of like when I went to go actually do the normalization, my first go-to was Wikipedia. Wikipedia said that JFK had roughly 30 million people processed through, and BWI had about 12 million. So that's like a factor of 2, right? JFK is twice as big as BWI according to Wikipedia in 2016. And then, and looking back at the data source for this came from the FAA, Federal Aviation Administration, the people who like monitor and secure all of our airports, right? So that's a pretty reliable FAA.gov website. So then I look at the BWI reporting, just to like verify is it consistent. And BWI says they processed 25 million people per day, or sorry, per year in 2016. So 25 million through BWI from their own website is not consistent with what Wikipedia is. And so at this point, I throw up my hands and say, I would like to normalize, but I don't know exactly where to get the accurate data from. So when I actually tried to do it, I was sort of like blocked. Okay, so a little bit of tangent. Did anyone have any questions? Normalization is, again, tricky to know when it is appropriate to use. I want to make sure everything is the same. But in this case, it would have been nice to make sure that JFK and BWI were really being compared on an equal footing of number of passengers processed. Okay. I'll try and emphasize or bring out other points or examples of that in future classes so that we can have that issue a little bit more solid footing than I've currently got for it. All right. And then just as a reminder myself, I haven't seen too many people use doc strings, and we'll be presenting that in class in a few of the notebooks. So I've put some links in here so that if you want to read more about those, you can come back. It's a way of commenting your functions that is in Python rather than in the Jupyter notebook. All right, so that'll be available via link. All right, so we have gotten roughly halfway through the semester, so congratulations. This is where I'll be releasing the stickers. We have dinosaurs and all that other good stuff in here. All right, so we're going to be doing a lot of hands-on stuff, and I'll be avoiding most of the theoretical stuff. The feedback that I've gotten from other data scientists is that the most common weakness in the data scientists they interview is in the mathematics skills. So I only have one class on it. This is an introduction to data science, not math. But so I would recommend if you don't have a strong math background, like you haven't taken calculus or linear algebra, there are lots of online courses. And the reason for that is math is, 400 years old, you could say, and like pretty well established. So there's lots of online courses and free resources. I'll be focusing a lot on the coding today, even though the complaint from data scientists is that more math and statistics is needed. So all of these will be sort of like demos and hands-on stuff. So the first touch here is on the role of math in data science. Like, why do we even care? And like I said, math is super old, and it has lots of different sort of silos of activity that are going on. And so data science typically touches a bunch of those domains. So linear algebra, who here has taken a course in linear algebra? Right, like 30% or so, right? Who else in statistics? Whew, wow, all right. No need for statistics then. If you guys get bored, because there's a lot of statistics here, let me know. All right. And then probability, that's pretty useful for creating models. The last two, calculus and ODEs, I won't touch too much because I haven't seen much practical use unless you're like developing machine learning algorithms from scratch, right? Like if you're in the land, that's cool. I'm not going to be there with you. All right. So again, math shows up all over the place in data science. And so all the different phases in the data science process have some basis in counting things typically and grouping things. And so that's where the math sort of wanders in. The problem is, even though data science is super heavy on using mathematics and implementing it, when you're telling a story to a customer, they're typically not mathematicians. And so your responsibility will be to use and apply the mathematics, but then be able to translate that back into a story of pretty pictures and like business impacts. So that's your responsibility as a data scientist. If you expect someone else to do that, you probably won't be as successful. All right. Like I said, it's huge. Math is a big field. This comes from like a YouTube video that's pretty good about like wandering through all of the different domains. I recommend that one, which I think is linked in the notes. And then the thing, as I've emphasized for other sort of like programming aspects, you have to figure out for all these different free resources, what is your style of learning and what is the book or course that you're using trying to teach. And if those aren't matched up, you're probably not going to have a lot of fun. So there's plenty of resources. You just have to evaluate all of them to figure out which ones fit your needs. All right. And by the way, UMBC is like known for its mathematics department, so it's a good place to learn math if you want to find somebody who knows what they're talking about. All right, so we're going to narrow it down a little bit. Statistics is a subdomain in mathematics, and so it's super useful because we have a bunch of mess and we want to clean it up in a rigorous fashion. So that's what statistics offers us. And then, let's see. Yeah, so I think that's all I wanted to sort of like clarify. Why do we care? So to get started in this, you're normally not handed a pile of numbers. Like you may be, but first you have to sort of like take the data you're given, which is usually human generated or sort of like large scale text. And so figuring out how to operate mathematically, that's like, at this level of, is it discrete, is it continuous? And you usually have to apply your knowledge and skills to take the data that you have and convert it into something that you can operate on. So you're typically not handed clean data with the right data types. And so you have to figure out, is this discrete? Right? Is it word categories? Is it unordered? Those are things that you'll have to break down. So we're going over a couple of these today, and this is like reasonably straightforward stuff, so I'm not going to spend a bunch of time worrying about it. But the part that will trip you up usually is the fact that we have continuous variables, but we have computers which expect discrete things. And so trying to figure out how to do that transformation without loss of information. Like you want to make sure that when you go to the discrete description of an event, that you haven't lost the information that's important. So we usually do that without even noticing, right? So like, for example, if you look at this set of eyes and I ask you what color are those, almost all of you will say blue, right? Like I may get some outliers here, but the assumption here is that we can make these things that are continuous, right? Like there's no actual single one color in that picture, but we put a label on it and make it a discrete variable. That makes our job easier, even though it's inaccurate. So this is something that you'll run across quite often, is that we make things discrete to make our analysis easier. Right, and that rounding is sort of like the trick that we use. All right, so that was my sort of introduction section. I'll talk a little bit about probability, and we'll do an exercise. All right, so I said statistics was how we sort of like make sense of the mess, and probability is the way that we sort of build models to describe the mess that we're looking at. All right, so I think everyone here is familiar with deck of cards, so I didn't bring those as my demo. But if you're not familiar with it, it's basically a set of paper, like very small. Oh. All right. So they're sorted into like 4 categories, and each category has 13 sort of numbers associated with it. And so they have 52 total cards in a standard deck. And so when I ask a question, I can either do an experiment, right, or like use your intuition. And so in this case, I'm going to use your intuition. That if I ask this question, anybody have an answer for that? Okay, so we had our 4th. Anybody disagree with that? Everybody's good on that? All right. So even though there's 52 cards, each color, there's 2 colors, but the trick is that the probability is just, there's 13 choices out of 52 total options, and that's for each heart, diamond, club, and spade. So 1/4. All right, so this was sort of like intended to be a physical example. We can also do similar things with Python. I think most of you have used the random library, so we'll do a quick demo of that. Random. What's it called? Getting started. All right. So who here has used dir command, dir? Okay, a couple people. That's pretty good. So if I'm in a new Python environment, the dir command is just going to tell me all the variables that exist by default in Python. So that's the output list here is all the variables that just are in the background that you typically aren't sort of wary or cautious or aware of. But the other use of dir is to tell you for a given library. So I've imported random. I'm looking at what's in that. I can use dir to see what the commands are from random. So most of these I don't care about, so I'm going to scroll past the ones with underscores. Down here, this is where like the useful things typically are, right? So like all of these variables are things that I would typically want to call in a notebook. And so you can discover those either by reading the documentation or within your Python notebook running the dir command. All right, so again, I think everyone has used this, so I'm not going to spend too much time, but you can make choices and add managers. This will be useful on your homework if you haven't seen random before. Foreshadowing. All right, so at this point, we're going to take take a break from the lecture part to grab your name tags, grab a penny from the table, grab stickers for your name tag. Right, the stickers are for your name tag, right, by the way. This will be a permanent choice that you're inflicted with for the rest of the semester. Wow. Make your choice wisely, right? Because this is something you have to live with for weeks.
That's a lot of pressure.
It is, right? It's like a life choice. Have a piece of paper and a penny to take back to your desk.
I'm definitely going with that.
The world's your oyster, man. A sticker, a penny, your name tag, and some paper. And if you don't have a pen, you'll also need a pen. Ask me for a pen, and I'll grab you one.
Do we put the sticker on?
On your name tag, that's where we're going with it. Yeah, sorry, I didn't make that clear that the sticker goes in your name tag. And it's not a requirement that you solve the problem now, but it's available.
Now, don't be brash. There's one variety. It's very important.
Can I take the whole thing?
If that's the kind of person you are, I can't do anything about that.
Whatever you want.
All right, so once you've got your penny, we have an exercise for you. Remember, I'm a poor professor. I will need the pennies back, so do not pocket the penny. Yes, I have them back. All right, so you've got your penny at your desk, you've got your name tag, you got some stickers, you're feeling pretty good. You take your piece of paper and you flip your coin 10 times and write down the results of your experiment.
Thank you.
You're welcome.
Here we go.
If you need help flipping a penny, should I teach you around here? Like this is the fancy version. You can put it in your thumb, flip it, and catch it. That takes a lot of coordination, especially if you're gonna watch that. There's just like drop it, give her a drop. That's lazy stroke.
Is there something about random, like where like computers can actually generate random numbers or something like that?
They're for like for true randomness. Yes, they're not that good. They're good enough for many things, but it depends on like how big you're going. Like if you're doing a lot of random numbers, then there can be some patterns that you didn't want. Like if you just say, I just want one number, probably gonna know.
Gonna be good enough.
Yeah. But if you're doing things at a large scale, it can be a problem. All right, so while you're flipping, I'm going to talk. Hopefully I won't be too distracting. So obviously, if you flip a coin once, there's two possible outcomes, right? Pretty straightforward. If you flip 2 times, there's 4 possible outcomes, right? Heads, 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 tails, tails, heads, or tails, tails. So you can do this whole counting game, and what you find is that in general, if I flip the coin n times, there are 2 to the n possible outcomes. Now, this is like a kind of abstract idea, so what does it actually mean? When I flip the coin 10 times, which is what you're doing, that means 1,024 potential outcomes. That seems like a lot. We're only 22 people, so we can't cover that entire space of all the outcomes. If I do 20 coin flips, which is a perfectly reasonable thing for a human to do, there are 2 to the 20th, which is 1 million different outcomes. Right, so that's a lot of outcomes. I'm not going to have you write down all of them, but that's the thing. So it sounds like the penny flipping has quieted down, so it sounds like we're ready to move on. All right, so now we have a challenge for you. And I don't know if I have everybody on here. All right, so if I don't have your name on there, I apologize. So the challenge is you just wrote down an experimental outcome. Right? The goal now is to write a Python program which simulates that environment and finds that experimental outcome.
Like it's mirroring it? Or?
So right, so like you found a pattern from a random set of sequences, right? The challenge is, can you do that in Python? All right, so there are pairs of names up here. That's your partner for the exercise. And I think Travis is not here and Dan is, so Dan, you will be Travis for this exercise. Who's Travis? Travis and John Jim. So you're with John Jim.
Yeah.
I got a really weird
The undiscoverable. DJ is over here, so DJ, you have to actively find your partner. Just wait for your partner to show up. Yeah, there's plenty of room, so you can spread out. Not everybody has to be at the center. Yo.
So when I think about we were looking at
I'll be wandering around for questions.
So, you know, just the call. So it's the you're gonna simulate and obviously what I'm thinking. Yep. I don't know. Basically,
I'm gonna rely on you a lot for this. Well, I think I know this one. We understand the deduction. So probably, so you write down where is it? So the goal is to get that and so the step 3 there is basically like how many, like in your virtual pipeline, or how many points would at the same time that's how long. Let's say the list is. Exactly. And then the question is like, how many? That's right.
So do you,
I think that's what I have.
Collaboration.
Okay, so we're thinking about, this is now, so we're gonna find out how many, so this county. So if I input.
I'm going for this. So
this is,
I did count some fixes and then I
saw the IS.
So I
So
think
it
more-
was- version was comp
So I
sci.
did before I understood the
nested, not nested, but just that way.
Nope. But I didn't take a comp sci.
Maybe I'm not sure. I usually have that, like, I'm not like fine until I get a table. I have a separate point of view. I'm supposed to be like animals, just like, or stress level.
Yeah,
Well,
right,
that's just-
I was just gonna say.
So,
That's why.
so if you put sort of a Python point, how many times do you need to put that point? You just need to see what that's a different, that's a slightly different question. I think that's describing.
Right,
Like,
because they.
yes, it was. Order.
Now you know.
I can find the question.
Yeah, I feel like. I feel like if you
Yes, I'm gonna go through and then, I'm doing, run this, it's fine. Just so, get one more hard.
Design code.
Yeah.
You guys have it?
It's good enough.
Alright, how's life?
Oh, I see it. Okay. Let me know how I can, and make sure whenever you come out, whenever you make help. Play it on your phone. Just try.
Oh,
yeah.
Yeah, I don't know.
Yeah, I was gonna ignore the definition stuff because this one. I was gonna try and make the definition.
What's the flex?
I mean, do we want to put the coin and keep scales? Yeah. Do that.
Yeah.
Yeah. So like what happens if you here and then just everything else like ahead and then start back over.
Seems like you're gonna construct a new tree.
So when you do that, if you're gonna generate those, you're gonna have to count each other. Why, thank you.
Everything's funny.
Well, you're looking for. So you're gonna
Well, do we really want to put 10 and then compare, or do we want to?
Right, so.
How would that, it's like, so, these 5 years, right? And this one, Red Tails, is even more than I think. Yeah, so I was a little bit.
Because of this point, in the first place, I probably would generate that random sequence from characters. So if you were a library, all through a library, the data. So you're going to do some of this. Now, this is.
Yeah, I was thinking it's like, I actually like throw my like skull as far as. First time was not the United States, just playing like we're not suing
Ben, are we number one? You're the first dog.
Wait,
So like if you put.
You're flipping until you find the secret.
So I don't, why did you put them together?
And then.
So we'll take another 2 minutes or so, and then we'll figure out where everybody's at. So 2 minutes from done time. By the way, so yeah, you renamed that SDR to SDR research.
Just run it again.
So let's do a print after the res out of 10. Let's do a print of the res. But the error message is that the SDR has no attribute of 10. So I think what you're intending to do is create, well, you want to like make a new string of that. But when will this string end? So let's so first you have, rather than using stop and end. Yeah, that's correct. You're not equal. But but the issue is that you were building so res out of 10 was the append function only available if you're working with a string. You have to use a join. So I think what you want to, I think what you're trying to do is like make a list of the characters, merge them into a single string. So I think it might be easier to like to make a separate variable that's a list. Like list of yeah. Yes. So strings are immutable and you can't change them. So you can't like add a new thing.
Yeah, but that's a list.
So you're going to make a list of characters.
I just think just keep focusing on
Strings are iterables.
You could have been. You can keep that. I'm saying like you should add a new variable. That's a list. Like a list of characters. So then, I think like LSD is that and
You guys have a nice time. One,
okay, so
Oh, yeah.
that make jump.
And they lost OBJ too. Crazy. I couldn't do that. So the Browns didn't do it.
yeah, the number of point trips, so the number of times that you're calling
I'd rather have the first title ever.
Yeah.
Yeah, because yours is like, oh,
so your wild doesn't have a limit on the 10. It's gonna make this list longer and longer. Probably never. I think you can just separate things that like make half of each percent clear.
Like take it in the meeting.
So I'd say like a 4 would be good. You want to limit it to like the size, the number of books.
Can you put print? Like print. I don't know.
Yeah. Like this. Like print X.
Oh, so it's gonna set the variable I to 0.
yeah.
Yes.
I can do that. No,
So it'll make a list. Correct. And also one more issue. So things along with that your list is have 0 inside the while. Because every time you're gonna do that, something new. And that's where you'll want to construct the res. Now that after you finish the move, but before you go back to the top, you'll want to do the join operation to make that string.
Yeah, just put prints around random choice.
So like,
Take off.
I don't think it, to the point I don't think initializing res that you
And then take that. Take that one too. You take all that.
so I don't have to do return one.
no, so you want to do it outside the core loop. Like first you have to construct the list, then you build the
So I put
so the
7
syntax,
take
get rid of that aria. It's just res equals and then an empty string like
that. I just need to see how it's going.
So I'm not.
We're writing it going.
So when you flip your coin, you got
All right, so
this many heads. So how many times would it take to get there? I thought I knew. Like maybe it needs to be a function that flips until it gets 7.
yeah, so that number instruction 3 is define the sequence of use of.
So this needs to like
All right, so we're gonna wrap up this part of the exercise. Does anyone have like a numeric result that they want to throw at me verbally? What's the number?
3066.
3066. Okay. Anyone else have a? How many times do they need to put their coin in Python to get that sequence?
Or I had like 9 heads.
I think that was probably a mistake.
It's hard.
Right. I mean,
Anyone else? Nobody solved it, and like nobody finished the notebook is my assumption.
We're number 1.
That's fine. So, all right. So I think at this point you can go back to your desk, and I will show you one solution. Oops. All right, if you feel bad for not finishing this problem, it's something you can totally work on at home, but I'm not going to be grading, so it's like I can offer you feedback, but it's not an assignment. Coin flips. All right. All right. So as an example of what the intention was, is that suppose that I flip a sequence, and here I'm going to use 1 for heads and 2 for tails. So I have this sequence of 4 numbers, 1, 2, 2, or 1, 2, 1, 1. And I want to figure out how many times would I need to flip a coin to get that sequence. So the way that I implemented a very verbose solution was I said I'm going to create a function that creates a random sequence of coin flips. So I can say what the length of the sequence should be and how many coin flips to make. Let's see. So I'm going to flip a coin a certain number of times, and then the coin flips count. I'll increment it every time that I flip a coin, and I'm choosing between 1 and 2 for that coin outcome. And then I'm creating the output of this function as a list. So I say this run, which is my list, I'm going to append the outcome of that coin flip. So basically, this is a piece of paper where I'm writing down the outcomes of the coin flip. That's the purpose of this function, to basically do the experiment. And then the challenge is do this experiment a bunch of times and figure out whether whether the output is comparable to the list that I had. All right. Oh yeah. So the other thing is I'm using a doc string here. So that's the triple quotes and then I close triple quotes within the function. So this is a way of documenting what the function does. An alternative that's sort of Python specific, rather than using Markdown in your notebook. So if you see that, that's a thing. I won't use it too much in this class. I have a couple notebooks that show that, but it's just another option to be aware of. So then I said, and this is my function where I had searched through calling that create random sequence a bunch of times, and then see whether or not that sequence of it that I originally flipped matches the sequence that I did in the function call. And if I find that there was a match, then I break out of the loop and I say the number of coin flips to match this was in this case 112. That's sort of like the logic of the program. It'll be available in Blackboard after class, so you can take a look at it. And then so you can just sort of like put in arbitrarily long sequences of coin flips and see how long it takes. The fun thing to me is like, and this is why I like programming, I guess, is because you can run through this a bunch of times in Python very quickly. I just think it ran. Right, so for a sequence of length 13, I can throw that in there, and that runs in 0.7 seconds, even though it's doing 91,000 coin flips. So this is like, why do I program? This is why, because I can't flip a coin, in a day 91,000 times. So, all right, and then I think I can visualize that, and just this is like a little geeking out, right? So like, I can do that same function, and I can count how many times the coin came with a certain outcome. I'll rerun all the cells. And so for my coin, I run this. See, so here I'm just flipping it 50 times, and my outcome, right? It's not always the same. It's going to be, it should be around 50% of the time heads and tails, but even for a fair coin, it's not going to be perfect every time. And so we can sort of like make that difference smaller if I increase the number of coin flips. So here I've got 500 coin flips, and there I got a number of heads and tails. It's pretty even. But if I rerun this notebook, it'll have some other outcome. So every experiment that I do is going to yield a different result. All right. And then one more sort of like cool thing before we go on break. This is a website that's available, and you can go to it and see how code works. So I'm just going to take that Python code that I just showed you about having a function where I do a coin flip and get a sequence, and then I test whether that sequence matches the one that I provided. And then on the right-hand side, it's currently blank, but there's a little stepping bar down here at the bottom, and it says there's 309 steps. So hopefully this boggles your mind, because when I first saw it, I was like, holy crap. All right, so I hit the forward progress indicator, and it moves down the sequence. So it just created a, maybe a little bigger. So it created sort of like a visualization of what the program is doing in the background. So as I step through this program, it's saying, okay, now you're going to go off and make an array of size 4, and there's going to be values 1, 2, 1, and 1. Right? And then the next step in the Python program calls this function. Right? So this is our stack of memory with all the variables that we're keeping track of. Whew, how's this start? This is from the website. So this is all the magic of the website that I'm.
It'll do this automatically. You don't do anything except
You paste your code in and say visualize execution. Yep. And so this is like this is really useful for building your intuition as to what Python is doing behind the scenes for you. so that when you're running your code, you can sort of have a better idea of why is the code behaving the way it is. Right, so here I created, in this line right here, line 13, I said this run is an empty list, and I can see that that was created, and it's telling me what Python's doing in the background. So now I'm going to enter the while loop, and then it's going to go up to that function. The first function call creates a new sort of like memory space because all those variables in the function are local to the function. So that's why it's creating this separate block of visualization. Right, so now I create an empty list for the function. I increment my index, I flip a coin. Right, this is what my program is doing. So I'm not going to step through all 309 Python steps here for execution, but you can basically step through yourself and see what your code does. It's a really useful way of building up a mental model of your code execution. Questions on that? I'm glad that some people are actually excited about this because like it's super useful to build that intuition. Because like normally, if you're just programming, you'd have to like build up this interior mental model yourself. It's a little difficult, no joke, right? So, all right, I think break. So come back at 8:12. And we'll come back and talk a little bit more math. By the way, I take back your pennies.
That's what I'm looking
So,
I like the bear with the little tag. You got these on sale. Christmas, Halloween. Got more? Sorry.
Dana.
Oh.
Nice to meet you. What? I know.
like you said, I'm not trying to get. That's exactly. What we-
Did you do it on Sam, right? No.
Yeah, I got more sticks.
So I wrote down my. Okay, so we do this, and then blocked out
What that, I call it a red line, what that red line.
You can always use the pen to get more.
That's just doing.
Guys are back for more stickers? What's up?
Yeah.
There's a lot of choices here in life. All right. We're not sticking to the 812 timeline. All right.
That was like 15 minutes. It was like 8:10 when you said that.
Oh, well, on this clock, it was 8:08. How long is a reasonable break?
I would say
5 minutes? Okay. Doable.
if you count from that. You want to count from travel? You wanna count-
Travel time. I was able to get to the bathroom. There's no eraser.
You walked in at 13.
It is true. I was way late.
And then-
Yes. Huh? So I don't know if I've told this class, but y'all are basically my guinea pigs. So that was an evaluator from the graduate school to comment on my teaching ability.
You're doing a great job.
Thank you. You'll have the opportunity. Yeah. So there will be a separate opportunity later, like a few classes from now, to do an anonymous feedback rather than telling me. So that'll come.
Yeah, but I didn't know.
Yeah, I need to build my ego for sure. Yeah, I do appreciate honest and direct feedback, but I know that's somewhat challenging to provide from a student perspective because of the power differential and the grading aspect, right, and all this other good stuff. So anonymous feedback is pretty useful. All right. Yeah, so I sort of jumped ahead without realizing it. Basically, all I wanted to show with this was that you can plot a bar chart in Python to look at the outcomes for your coin flips. And what that is showing is for just two outcomes, there's a uniform distribution. So they're relatively equal. If you had a bunch of variables or different outcomes that you're looking at, the outcome would also be flat, right, for all the different variables. That's called the uniform distribution. So that's like a really useful place to start. You can build other distributions from the uniform distribution by applying some transformations. Not in this book for this class, but this is like where you should typically start with any probabilistic sort of model. Okay, the other continuous variables again. So I'll be basically focusing on the binomial distribution because that's most of like what you'll be doing is a set of discrete events with independent trials, right? So every time that you flip the coin wasn't aware of what the last outcome was, and so it can't sort of like change its outcome based on the history. So that's what we mean by independent. You're using the same coin every time. That's the identical part. And then you're repeating that a bunch of times. Yeah, and then basically binomial by, right, two outcomes, and the outcomes are either going to be like heads or tails. And they could be 40-60, be 50-50 at that split of like what is the outcome. That's the P there that we're referring to. All right. So where this is going is that we can construct a bell curve using these coins. Not that I'm going to have you do that right now. I'm going to switch over to Python, and you'll see why in a minute it would be unreasonable to construct this bell curve. Okay. Binomial distribution. All these notebooks will be available to you in Blackboard. I'm going to restart all cells. This will actually take a little bit of time to run, because what we're doing is we're going to flip a coin 1,000 times. And then we're going to do that experiment 1,000 times. So that's a lot of coin flippage. That's why we're not doing it in person. The reason that we're doing that is we're trying to figure out, when I flip a coin 1,000 times, like on average, right, it should be roughly 500 heads and 500 tails. Right? That's like the naive assumption. But it might be that you get, 400 tails and 600 heads, right, or some other mixture when I do 1,000 coin flips. And so I need to do that trial many times in order to figure out what's the average, right? That mean value, but then what is the spread of, how many times we get 400 versus 600, how many times we get 500 versus 500, right? What is that outcome? So basically all this walks through, there's a little bit of list comprehensions that you'll be able to look at, but basically I'm building up this experiment to figure out how many times did I get heads. And so this is the number of trials in this axis, and this is the number of times I got heads. So you'll see that the distribution is centered around 500 times I got heads, which makes sense. And this width is sort of like, you can say, the coin, how confident are we about that outcome being fair? Because it could be, right, this is like probability. You could say, like, I flipped a coin 1,000 times, it was heads 500 of those times, so the outcome was like perfectly fair. Well, that's not an accurate statement, right? It happened to be that in that trial you got that even distribution, but most of the time it'll be slightly above or below that. Right, so we can play around with like the display of that by setting the axis to be focused on the range we care about for the number of outcomes, and then we can set the number of scrolled off the screen here. Yeah, the number of bins here I've increased to be the number of coin tosses per trial, so 1,000. So, and then I labeled my axes, which is good. Then the previous one I apparently forgot. And then there's other libraries where you can use Seaborn, and that actually does the fit for that automatically by default, so it's kind of handy. If you haven't used Seaborn, it's definitely more beautiful than the matplotlib output that we would normally use. Okay, and I think, yeah, I didn't get back to, so I wanted to do error bars on my original plot, but I didn't get to that, so you'll be shorted that outcome. So the point of all that sort of like quick discussion is that, let me get to the next slide, right? So using the same coin, we got this outcome, right? A bunch of trials leading to these various results. What's the relation between these, right? Like this is one trial, and this is the outcome of a bunch of trials. So we can get a uniform distribution versus a binomial distribution. So there's some deeper meaning to that. And the answer to go back to like what is the relation between these, and unfortunately I didn't plot the error bars for this original curve, but there's a confidence interval of like, this was, the outcome here is slightly below 250, and then it was slightly above 250. That was for one trial. But typically we want to label the confidence interval of an experimental outcome. And so the way that we do that is we run a trial a bunch of times. and then we ask like, what are the dimensions of this shape, and that will tell us the confidence level of these, and they'll put error bars on them. So it's like the high level view is that you get error bars from doing a bunch of trials, right? And then the details behind that. A confidence interval, that's the error bar that you typically put on a bar chart. That's telling you how certain we are about the average outcome. So the more trials we do, the more certain we'll be about the outcome. So you can change your confidence level by doing more trials. That's like a relatively straightforward discussion, I think. Where that gets a little tricky is that bell curve. There are parameters associated with that, like variance, standard deviation. You may have heard of those. Those don't change as you increase the number of trials. So the shape of the curve is constant, hopefully, as you do more and more trials. So the confidence level goes up, and the standard deviation and variance do not change. So the reason for one of those changing and the other not is because confidence interval is really a measure of how much area is under this curve, and the actual shape of the curve, which is what the variance and standard deviation are saying, those parameters don't change. So how much area is under this curve? That's where the expression like 95% confidence interval. It is the area of that curve. So you can sort of like understand that the more trials you do, the more area you're going to capture. So you'll have higher confidence in that outcome. I think I'm slowly losing people. So questions on that? Okay. All right. So we've been talking a lot about experiments. It's the way that I live my life, but it's not the only way to live your life. Because sometimes, like for geophysicists, they just can't replicate the Earth, right? They can't do an experiment with another Earth. So what do you do then, right? So, or maybe it's really expensive to do that. So so what I've been sort of presenting to you is what's called the frequentist approach. This is like do a bunch of experiments. They're all independent and they're the same, and so therefore we can build up a model based on that. There's another class of people, another sort of religious camp, called the Bayesianists, right? The Bayesian interference folks. They're trying to figure out without doing all that work. And so, in one sense, you could say the Bayesian interference people, they're trying to figure out what the answer is without doing the work. So there's a bit of risk there, right? That the assumptions are wrong. And so they spend a lot of their time validating their assumptions, whereas the frequentist people spend a lot of their time running the experiments.
So are you saying that they start backwards, so that they start with the outcome and look backwards?
Yes, I think that's. I'm not going to speak with authority, but I think that's correct. So yeah, so there's two different ways, and basically it's like where do you want to spend your time working, right? Building the model or testing the assumptions. That's it. Okay, so now we have like a fun little diversion over correlation. There's a bit of like a funny part in here. Hopefully you laugh. All right, but to get to the joke, we have to do some math, so I apologize. All right, so what I was talking about earlier is that variance, that's the width of that bell curve, right? That's for a single variable, right? In this case, we're doing coin and flip outcomes. That was the single variable we were testing. And so that's this picture, right? Sometimes we want to know the relation between two variables, and then we talk about correlation. And so correlation and variance are related, and they're related by this like bridging term, covariance. So let's talk about covariance. It's joint covariability, which that's the alternative word for it. All right, so what is this covariance concept? So here we have two parameters that we're measuring, x and y, and those outcomes can part as these little dots. Those are the values for the two variables for a given event. And somewhere in there, there's like an average value for the x, the expectation value for that x variable, and there's the average value for the y, the expectation here. Right? And so that defines the center of our distribution. And then what we really want to measure at the variance is like how far are things from the mean we want to do that in 2 dimensions. And the way to do that is to say, how far is this point from that center? One way of setting it is to say the area of this point to the center is marked up by this pink square. And the other area over here from that point we'll call another different area. And then these points are blue because those are negative, right? So we have to introduce positive and negative areas. So it's the 2 different colors. And so basically you sum up all of these different areas, the positive and the negatives, and then you call that your covariance. So it's a measure of how spread out are things in 2 dimensions. And then you can take that area, like I think I said, yeah, so back here I was saying like covariance is the sort of spacing out of things in 2 dimensions. And then you can normalize that to between -1 and 1, and that's your correlation. Questions on that? That's the concept of correlation. Now here's the fun part. So you can say that there are 2 variables, right? What's the divorce rate in Maine, and how many people are consuming, or the per capita consumption of margarine in the entire United States. And it turns out if you take those 2 variables, they're highly correlated. You'd say, I discovered a predictor, right? If I wanted to figure out how many people are going to be consuming margarine, I just need to look at the number of people getting divorced in Maine. Okay, can anyone explain why that happened? What was that? Eat more food. No. Anyone else? Why did this happen? Okay. So the reason is if you look through a large enough data set with enough variables, you will find things that are highly correlated. And so there's a whole website, which I totally recommend you should definitely visit, where it just has like random things that are correlated. And there's no actual like justification, like there's no like causality. It's just that these variables, if you look at enough data, are correlated. So, question? I see what I'm forming on the lips.
So you're just saying that basically that just because it was correlated doesn't.
Sensical, right? Yes. So if you look at enough data, you can find coincidences. A good way to think about it. Right, so it's a harder claim to sort of figure out, is there causality between these 2 variables, right? Does this thing cause the other thing? And that's a much harder test to apply. So don't get swayed by correlation.
Although the butter one might make sense if people take that.
I don't eat margarine, so I can't really comment on that.
What about the not
That also turns out it's not a good cooking substance. I do cook. All right, so where that was sort of leading to is that math and counting are objective activities, right? Like you can count a thing and someone else who counts that counts the same result, right? That's why it's objective. But the problem is you can use these tools in inappropriate ways to miscommunicate. And that's sort of like the lesson here I'm trying to drive home. So the trick to doing that is to know what all the problems that you could run into are before encountering them. Because if like you don't know what the problems are, you're most likely going to encounter them, and someone else will have to point out to you you're wrong. Right? Or you can like intentionally mislead things, but I won't cover that. That's a different like ethics class. Okay. Right. All right. So there's a couple of problems that we typically run into in data science, like trying to figure out what all the answers are doesn't work because it's expensive and takes a bunch of time. And so we make our jobs easier by looking at only a subset of things. And so that saves us money and time, makes our job easier, but introduces risk. And so there are many lists of biases that you can read up on. This is just to give you an example of like the traps you can fall into. I'm not going to read off those, but basically you need to have some conception of like what the traps are relevant to the data you're looking at and the problems you're solving, so that when you do your analysis, you know what to avoid or what to account for. So the point of this slide is to arm you with the question in your head of what should I be watching out for when I analyze a given data set? And because I can't tell you what all the biases are specific to your data set, that's going to be your job. And typically, this isn't so much of an issue if someone just like hands you a pile of data, like I've been doing, right? Because that's what the data said. That's all we have to go on. But this is more of an issue when you're designing an experiment or you're designing some data collection system, which you will invariably do as a data scientist, right? Like, it won't always be the case. You just get handed things. So you'll be designing experiments and collections, and that'll be a challenge. Okay. All right, time series. The next lecture, by the way, is on time series. So there's going to be a slight sort of like taster of it, because it's a pretty big field. All right, so this is a little reminder that a lot of what I do in my work is I go off and talk to people. And the reason for that is because even though people throw a bunch of data at me, like a lot of time series, my ability to understand that data is heavily influenced by the folklore that I understand from people. So there's one of the ways that I get folklore is I talk to people. The other is I have an internal model of what the reality is. And those two sort of like build on each other. So what I'm going to be doing in a few slides here is to ask for your folklore, right? You have internal knowledge based on the fact that you've lived here for at least a few weeks. And like you have knowledge about how this environment works. What's the next slide? All right. So if anyone needs paper, let me know. But what I'm going to ask you to do is we're going to look at some power data, electrical power information. And the axes for the plot that I want you to draw on your paper are time and power. So ask me questions that you want. I will dispense answers to them, but I want you to draw a picture of what the power looks like for a function of time on the span of days. Yeah, that makes sense. And this is for the scale of a city. Sure, you could say one. Questions? It is irrelevant, but we'll call it January. Does anybody have questions? I mean, I'm hoping for the question here. Does anyone know what a megawatt is? No, okay.
This is 1,000.
That'd be a great, yes, it is 1,000 kilowatts. I'm not going to blow up.
Knowing the definition is different.
Yeah, so knowing what it is, it's a different question. But so it is a measure of electrical power, right? And so I think I'm not going to go out the limit. I guess your house would consume like hundreds of kilowatts, no, tens of kilowatts. All right, so some number of kilowatts is how much your house consumes, and a large city will have a few megawatts of power consumption. That does not tell you what it feels like, right? So from a financial perspective, the cost of a megawatt of electricity is $1 million per year. That means so our local energy provider is Baltimore Gas and Electric, PG&E. So if I went to PG&E and said I need to buy a megawatt of electricity for a year, they'd say, where's your $1 million? So that give you a rough scale of like your electrical bill for your house versus how much it would cost to buy a megawatt of electricity. $1 million per year. Not accounting for all the financial shenanigans they put. All right. So does anybody have a plot that they'd like to share? Let's see, DocCam. But if we can get it up on the DocCam, I'll be super happy. But not guaranteeing that. Source. DocCam. Oh, no. All right, DocCam may not work because HDMI is dead, but let's try this one. Okay, came up. All right. Who has a plot they would like to share? John, hop on up. Okay, the point of John's demo here will be for him to defend his logic and explain what he did.
That's barely any logic in it.
All right.
So, you want to play? Okay.
All right.
Ignore this. I was taking notes. Basically, it's just the number of days along the bottom axis, the power arbitrarily, like just kind of general level of where it's at. Essentially, my thinking was maybe if you're paying your bill monthly for a power bill, that after you pay your bill, you're like feeling amorous and you just want to like go crazy and take long showers or something like that. And then so like at the beginning of the month you're using more power, and then like as you get busy throughout the month, you'll probably like go home or something like that.
Okay.
Or like go out and not use as much power.
All right. So what you're expecting is that there'll be some average value, and there'll be some fluctuations around the average.
Mm-hmm.
And there's some motivation for why that fluctuation would occur.
Based on their behavior, yes.
All right. Thank you. Anybody else have a different plot? Hector. Come on down. So what we're doing here, right, is we're trying to establish what is the folklore around electrical power, right, for a city.
So I don't know if this is gonna. I don't know if you know. I know a little bit about. I deal with DHS, critical infrastructure.
What is DHS?
Department of Homeland Security. I'm sorry. So the way critical infrastructure, the way electricity tends to work, a lot of people don't know, is from the East Coast to the West Coast, because the electricity is needed at different times throughout. All power plants kind of work together to wake up different parts of the country at different times throughout the day. I knew that, so I figured with regard to a major city, what you're seeing here, those peaks here, these are the weekends, right? I imagine a lot of things, a lot of activity occurring. But with regard to the peaks and the troughs in between, that would be either like rush hour, waking up, things of that nature, until we get kind of like steady state point, and then rush hour going back home, at which point it's the peaks again. That was mine.
Okay. I love discovering that we have subject matter experts. It's always fun. So thank you, Hector. All right. So this is almost like an example of like if you talk to enough random people, you'll find someone who's an expert. So just happen to have one here locally. All right. So we got some feedback on some presenters. So there is internal sort of like knowledge that people have. It varies, right? Like John had an example, Hector had an example. You could tell what the different sort of experience level was in that. So thank you. All right. I'm going to look at a website. Happens to have. So there is a company called Exelon, and I think this is in Scotland, if I remember correctly. But so they very politely for you make all their data available. It's super awesome, right? And they go so far as to plot the live data for you. Is that amazing? And like what power company does this? I don't know, but it sort of boggles my mind. They made, in my opinion, like they made the fluctuations very clear by setting this to not be equal to 0. Right? So it's like it emphasizes the variance of this plot. That's cool. And the time scale here is pretty limited. Right? This is like, I don't know, 2 hours, I guess. So that's not very much data. Right? So you can say, well, let's get all the data. That's what we do in this class, right? So they happen to have over here, your default page here is the latest. There's a historic tab. Guess what that contains? All the data. So let's go over there. All right, so they give us this nice intuitive web interface, right, with a start date and an end date. So we'll get the weekend here, right? View, a fancy little web page loading thing going on. And then they present the data in a table form, which turns out is not that useful because like copy pasting this is a pain in the butt. But they happen to present it in XML and CSV for you to download. How convenient. That'll be your homework. All right, so we'll come back to that. I think I have some interesting sort of like observations of that, if I can pull it up. Maybe, what did I call it? I keep forgetting the name of my notebook. Visualizing time variation. All right. So I downloaded the data, right? And then, let's see, so, uh-oh, I think I may not have the actual data. Let's see if I can download it. So there'll be a slight delay while I get the data. Let's do that much. Oops, no, all right. This may or may not work, in which case I apologize if it does not. But try and get through it. Okay. All right, so paste that in there. All right, exciting. All right, so by default, they put in this time of measurement and the value. So this value here is the kilowatts. It's actually, look back in the plot. They are giving it, the plot is in megawatts. Yeah, so, oh, well, they mislabeled their data. Right? That would be 25 megawatts, which is 25,000 kilowatts. So ignore their incorrect label also. All right, so I had to do a bunch of sort of magic to read in the CSV. I will probably skip over how I got to that magic. And so then I forgot to run the notebook. All right, so I had to do some conversions, and then I can plot it, see what it looks like. Awesome. All right, so what we're seeing here, right, is the fluctuation as a function of time. That's really kilowatts. So can anyone have any sort of like observation of what's going on here? So can someone look up what day of the week was it on the second? Saturday. All right. So here we have a Saturday, Sunday, Monday, Tuesday. So you can sort of see the function of people were sleeping, right? People woke up. People were home probably in the evening and went back to sleep. So there's a 24-hour cyclic pattern going on here. And there's another pattern of the days. Right? So like days of the week, as Hector pointed out, are definitely important because people's behavior on Saturday and Sunday is different than it is during the weekday. So this is just to give you a snapshot of a little bit of time during data with some patterns embedded in it. Kind of a teaser for next week. Questions on that? All right, good. So that's, I think all I have on that one. There's a long sequence of notebooks that I went through to like build that up. And so my point in sharing these old notebooks with you is that if you look through these, you can sort of see, okay. I did the process of figuring out what's in the data frame, creating all the pandas commands to load this data. I'll fix this. All right, so I went and looked at the contents. That's what the CSV looks like. When I try and read that data from the CSV into the data frame, this is my default output. And so this notebook, the sequence of notebooks walks through the problems I had troubleshooting what I had to do to get the final output, right? So this final version 5, that's the exciting part that I showed you. And so it looks very concise, right? It says, do all this magic things, and then make the plot, and it appears. Very straightforward, right? But the hard part that I'm trying to explain that exists, because it's very easy to get caught up in, oh, it's very simple. Like, you only did one thing. Well, no, there were like 5 notebooks that I had built to get to that point. And so, knowing commands to use, I had to build up to that process. And so I'll share all these old notebooks with you, but they sort of walk through. Like the first problem I had is that when you read in the timestamps as they're given, you get this like weird plot. Like it gives you a clue that, oh, there's something wrong there. So trying to figure out what's going on. Slowly, all the logic builds up. I run into some error. I switch over to a new notebook, right? So that's the intention there. In the interest of time, we'll move on. If I can open it. All right. So the other exciting sort of demo that I wanted to get to is the Chrome analysis. So the goal here is that this is another time series, but it is of totally different data. And hopefully, again, this will be a little bit interesting for you because it's something that you can do on that you have. All right. So there's a couple links in this notebook as to how this process works. We'll restart all the kernel. Basically, on my computer, I use Chrome as my web browser. You can do the same project for Firefox, but you can basically get your history on your computer for your web browser, regardless which browser you're using. So I copy that into my local directory, and then if you're familiar with SQL, the Chrome history turns out to be an SQLite file. Okay, so that's like a nice data source because you have web browsing pattern of behavior, right, and you can investigate that as a data scientist using SQL pandas. Right. So basically, you can use pandas to open up your history file, run an SQL command, and get data back. All right, we're building with excitement, I can tell. All right. Sorry? Yeah. So it's specifically the file that we're connecting. So SQLite connect to that file, and we're going to call it a variable con, and then we'll call that as the reference. Yes. So that's what this next cell is. So So this was just to say I can pluck out time values in this format. That's what Chrome uses. And so this cell down here is the actual work where I'm going to pull out the timestamp and the URLs. That's an SQL query. I won't teach you that at this time. That's just to say that you can run an SQL query against the history file and get back a data frame. Here I have the timestamp of when I visited the site and which site I visited. So that's a nice table to have. Hopefully there were no naughty sites in it, right? All right. So then I printed the top of the file head and the bottom of the file because typically that's where your problems occur in timestamp. And for whatever reason, these sites are occurring back in 1600, December 31st. Highly unlikely. You should all squint and be like, what the heck? Very reasonable. So I'm gonna, first the both columns are objects. I'm gonna force the date time column to be a timestamp. And so when I do that, nothing much changes in the visual output here, but these become nans. So there was some other problem that wasn't quite registering. And so the question of how many nans were there were 13. Right? So I can figure out what the max and min timestamps were. So this history file captures my activity from December 31st to yesterday. And then there were 13 of the rows which had invalid timestamps. So for my purposes, 13 out of, how big was it? I didn't show how big the file was. Let's do a new, that shape. Not right. Oops, histdf. There we go. So it's 13,000 URLs in the past few months. Obviously, that's a lot of activity. So dropping 13 won't matter too much. Okay. So then what I can do with this data is I can plot how many URLs I visited in a given month. So here we have the bar chart. And here, unlike the earlier bar chart I was talking about where it makes sense to order it, here I would argue that the order does matter, and here it's incorrect. So this is because this is October of 2018, December of 2018, and then it moves around, so we're trying to order these. So the order is a little funky. Apologize for that. So The other mistake that you'll see here is that for some reason, there was actually only like a few days in October that were recorded. November wasn't recorded at all. And then like December, January, February, and March look reasonable. So why that is, I don't know. All right, so we can do some fancier group by operations and get this year to show up. So those commands are there, but basically I can say 2018 in October and 2018 in December, and then let's get the year 2019 for those 2 months. Now I've got the order fixed, and it looks a little bit more pleasing in that order sense. Okay, so those are functions that are there that you'll be able to review. Then I can do some fancier things. So I can say, what day of the month am I visiting the most URLs on, right? So this is ordered by days of the month, and this is URLs, which looks like a nice, pretty plot, but it's almost meaningless. And the reason for that is because like, this is the 26th day of October and December and January and February and March. Like, I wouldn't expect any pattern to show up. Like, I don't visit, well, apparently 21st is pretty rare for me to visit websites. It is the total URL for all of those 21st, right? So I don't have a good, so maybe the takeaway for this is like you can plot things, but they don't have a ton of value, right? It does make more sense if we plot, say the month and the day. So now we've got basically a per day plot for all the days, and you can see, I'm looking for December, here we go. So there's only one day in October that was recorded. That's why the October date showed up, but this is January, February, March, January, February, and March are here. That makes sense? So now we've got the day and month. That plot makes more sense. And you'll see like, there is this range of days where there's either like 0 hits or very few. That's when I was in Taiwan, but I didn't have internet. So like this is now a story that I can tell, right? That sort of makes sense to me. Okay. I think this last one is just hour or day, which is another fun story. So you can see like this is local time, and so the hour here is like 6 a.m., 7 a.m., 8 a.m., 9 a.m. Right, so guess when I sleep. Apparently for those 5 hours. Right, but again, this is averaged over all of the data for all of the days for all of those months. And so this is the cumulative count at 10 p.m., right? So at 10 p.m. over the past few months since December, I visited 1,600 sites. So this is, why am I showing this? It's time series data, right? You can extract stories out of it by looking at sort of what I call the burstiness of activity. And so it's very clear when I get home from work is about 5, and then I do work on the internet, right? These are my searches at work. So cool, fun stuff that you will be using for your assignment for homework. Yes, Alex. I can check that and get back to you. I'm gonna guess SQLite 3. Woohoo! Yeah, so that's a library that I imported. Import SQLite 3. So. That is a good question. I don't have an answer for. You're asking, can I use SQLite against a CSV?
Right, CSV. Just because it looks like you can pass it through.
I don't. Yeah, I have no idea. I have the what? Okay. All right. So the whole, the point there is to say that for time series, there's lots of simple analysis you can do. In the next class, we'll be covering more depth on different pattern analysis. These are just sort of like a set of visual stories to tell just off of the data, and that's what you'll be doing in the homework assignment. All right, so I just showed you a bunch of histograms and bar charts. There's some subjective sort of design that goes into that. I don't have a rule of thumb about what the right sort of outcome should be, but it's, at least for me, intuitive to say, like, this bar chart has too many bins, this has too few, and this sounds just right. But the Goldilocks method of data analysis, I don't have anything better than that, so I apologize. Like, this is an issue you'll run into when you're doing the histograms. It's something you have to play with to figure out what the right answer is. Oops, is that all I had? Okay. That's the only comment I have on that, but we'll come back to visualizations in a sets. All right, so this is building off of the example that I just gave you. Like, the purpose of using sets in Python is typically to look for intersections or overlaps and measure that type of thing. So that's the question that it sort of leads you into the sets domain. Right, so a very simple example is like stuff I own now, stuff I owned 10 years ago, right? And that's the intersection there is like things that I've had in my possession for the past 10 years. So just to give you another example of where sets come into play in Python. So I think I have a little quick example here. All right, so many of you have already used sets in the previous homeworks, so you may not have encountered all of these issues though. So that's what I'm going to walk through it step by step here. So sets are basically a collection of objects that are unique, they're distinguishable. So I can't have a repeated object. So that's, and it's a little confusing because the set notation is using those curly brackets, which also show up in dictionaries, but dictionaries are not hashable, which I'll explain a little bit. So it's using the curly brackets that identifies it as a set. And so each of those entities, they're distinguishable according to Python because they have different hash values. And so something I learned when I was figuring this out is that every variable that has a unique hash, you can figure out what that hash is. And it's basically like a unique identifier for the variable. That's present for every unique entity. So typically we don't work with sets by default, we work with lists. And so you can take a list of things and convert it into a set. The consequence of doing that is that you lose all the repeated elements. So here I have 4 and 4 and then twice. And so when I convert it into a set, it gives me only the collection of unique objects. I just showed you that I can convert a list to a set. That doesn't always hold true. So if my list has a thing in it that isn't able to be made unique, like a dictionary is not able to be made unique because these values are dynamic, they can change. So when I convert that list, then it says it's unhashable. It's complaining that this thing isn't being able to be made unique, so we can't make this list into a set. So that's sort of like a little problem you may run into. If you can make a set, the reason that you typically want to do that is intersections. And so there's some syntax that didn't get executed here because the cell got interrupted, but make a set, and then we'll do the and. So this is looking for what are the things in this set and in another set. And then it returns the things that overlap from both those. All right. And then when I ask for the or, that returns the combination of all the things in both sets. But again, still unique. Why am I discussing this? Because the most common mistake that gets made is people use the Boolean and or. So they're distinct. This is the
ampersand and the bar, those are the set operations. These are the Boolean operations.
So what does that mean? Well, so follow me along in this little tour. You have two sets,
And I have this set of unique items and another set of unique items. And you'll see by inspection that some things are in both sets and some things are only in one of the sets. And so when I use the Boolean AND, what I get back is this thing. And when I use the ampersand, I get back to this set.
so they both return sets, but only one of them is what we usually intend.
The reason for that is the Boolean AND is just looking for, is this statement true? Is this statement true? Yes. Okay, then we're going to return the last one. So
It's a little bit of Boolean logic that can catch you up if you're not waiting for it. And so
this is the one we usually want to use to figure out where the intersection of the two sets is.
And the reason for why the Boolean returns something else, this is something I don't quite understand at this point,
but when you ask what is the Boolean value of the variable another set, that returns true.
that's why the expression returns what it does. I don't have a good explanation for the Pythonic reason for returning a Boolean value from evaluating a set. If anybody has any suggestions, let me know. Like none? That's a good, so like, I think what you're proposing is if I say bool none, I'm kind of curious. False. Thanks. All right, so the last tip here is that if you're trying to wonder what a thing does, like an operator,
You can use the help function. So this is distinct from the dir, which you mentioned earlier. But the help function will
tell you what's going on with that operator. Okay. That's a random collection of tips I have for sets. I think that's all. Yeah, okay. All right, gonna jump over it. So we've got like 35 minutes left, and we're gonna jump into NumPy and linear. I think we'll take a break for 5 minutes. Come back at 9:09.
And you go to like it's like half the classes in the back. Yeah. So that's the challenge is like if you get into like the very advanced math programs, you have to have like basic math and like you're just trying to get pretty much. Well, the thing is, it's like this is the shortest list, so I can take my whole calc in this class and then like basically like probably like 32. All these stuff. I kind of like well, you're about to tell me why it is, but like it depends on where the data is. I haven't fully sort of analysis. Yeah, you use it a little bit. It depends on what you want. Well, like am I initial so that's fine. And I realize
Oh, no, so.
All right. Thanks. Thank you.
Oh, yeah.
Okay, I think we got everybody back, so we'll get started again. Okay, so I was having a discussion during break about, like, you know, would you need the advanced mathematics? And the real answer is, like, it strongly depends on where within data science you're gonna try and work. Most of my work is with exploratory data analysis, not so much designing machine learning algorithms for, like, new purposes. So if you're going into the designing new machine learning algorithms, a lot of the advanced mathematics is totally relevant, and you definitely should be exposed to. For my work, I typically don't use a bunch of advanced mathematics because I'm just, like, cleaning data almost all the day, right? Like, that's my life. Visualization, cleaning data, that's where I live. So for my purposes, I use some of these tools, and for that purpose, it can be sort of comforting to know the mathematics behind the tool. It's not, like, deeply essential to understand, like, you know, why are we doing this operation versus this operation? Like, from my perspective as EDA, I don't care. Someone else solved that problem, so I don't have to. But it all depends on where you're gonna end up, right? Like, a lot of you, I hope, will be doing some advanced data science and machine learning algorithms, hopefully with your degree from this program. And so this may be more relevant to you. I'm just on the front end of getting the data, cleaning the data. Okay, so yeah, specifically linear algebra shows up in a couple different places. Again, a lot of machine learning focus, exploits the mathematics that's there. So the way that we typically do the linear algebra operations in Python is with a library called NumPy, which you've probably been exposed to quite a bit already, but maybe haven't flexed all the tools in NumPy. So the reason that we operate on with linear algebra is because it's like the way that we deal with basically tables of data, right? In math, it's called a matrix, but if you have
list, right, you can think of that as a vector, and if you have a set of two-dimensional arrays, call it a matrix, and if you have 3 dimensions or more, call it a tensor, right? Hence TensorFlow. So let's see if we can jump over to NumPy. Yes, it is. All right, so the value NumPy forces you to think about things a little bit differently because it's linear algebra. So typically you've been working with lists, and the operations that you do with a list are slightly different. So the first sort of distinguishing characteristic is that vectors all have the same type as the elements, whereas a list can contain a bunch of different things. There are things you can do with vectors you can't do with lists by default. So like if I tried to divide a list of numbers, or even like this list up here, by a scalar value, that wouldn't work out in Python, but that is well defined in linear algebra, so it is an operation you can do in NumPy. So that's sort of like the it requires a little bit of change in thinking, but it depends on how strong your background is in linear algebra. So in addition to arrays, you can construct matrices. Again, they're probably not totally relevant to the work that we're doing in 601 here, but they will be useful for if you're in 602, if you haven't already explored that. And so a lot of the things that we see in pandas are from NumPy, which goes back to that question of what's the relation between the two. So for instance, you can ask, what is the shape of this NumPy array? And it gives you the number of rows and columns. So that should sound familiar. So a lot of the things do carry over, like indexing from 0 in a list, same thing as indexing from 0 in NumPy. I think that's all I have on that. It's just to get you realizing that like NumPy is different, even though we exploit it under the hood when we're using pandas. We don't sort of like worry about that fact. Has anyone here like used NumPy in anger, as they say? No. Okay. So I think hopefully if you progress through 602, hopefully they expose you a little bit more to doing linear algebra operations in NumPy. But again, that's more focused on like designing the algorithms and implementing them from scratch, which most people do not do. Okay. Oh yeah. So if you are curious about like, I have no exposure to linear algebra, what do I do? There's tons of online courses for linear algebra, and a lot of them do start from like the very basics, but some of them like ramp up quickly into like, this is the theory, and like, so it depends on sort of what you're looking at. If you need recommendations, let me know, but again, it strongly depends on where you're coming from in your educational background. All right. The calculus and differential equations, don't worry, it'll be about as short as the NumPy version, right? So again, we do use calculus and data science, and we do use partial differential equations and ordinary differential equations, but they're not exposed to you if you're using pandas typically, right? Someone else has done the hard work of implementing these libraries in C, and then you get to call them from pandas and not even worry about how it executes. So it's like the value of an abstraction layer is that you don't have to worry about someone else's hard work. And this is like the rate of change is like, that's the big takeaway for differential equations. Like if we want to look at how something is evolving and you care about the rate of change, that's where your differential equations come in. Right. So where that shows up is in optimization, which is used extensively in machine learning to find out, is my training of this model improving the outcome or not? It's like a standard machine learning use, but again, not typically exposed to the people who are using the tools unless there's some underlying flaw. There is value, like I said, in understanding the reasoning behind these tools so that you can say, like, it is appropriate to use this method or not. Right? You're typically not going to attack the optimization of that implementation. It is worth knowing whether it's a relevant approach or not. I think that's pretty much what I have to say. Yeah. Okay. So like I said,
my day is not filled with that type of work. So I will tell you what my day is filled with. Mostly emails and meetings. So if you're like excited to go into data science, like write code and solve problems, and like then you get into a large organization, that probably won't be your life. Kind of like sitting down every day and writing code at the computer, like that is a thing that I do, maybe like an hour or so a day. But a lot of it is spent coordinating between people who are doing different things and different projects with different backgrounds, right? So I work with like electrical engineers, mechanical engineers, computer scientists, mathematicians, right? All these people speak different languages, and the data scientist is often turned to as the person who bridges the different problems, right? So that's a communication effort because you're expected to have a background in math and domain expertise and programming and able to implement solutions. So you are the unicorn that does all the things. Therefore, you communicate with all the people. Therefore, you get less exposure to actual technical time, hands on keyboard. So this is sort of like the tension that I have to balance is I want to remain technically relevant and capable of doing actual things and also be able to pivot the organization in a way that I think it should move. And I can't do both of those things at the same time. So finding that balance is a lot of my work. Any questions on that? Yes.
So, as a developer, my career path would be getting up to senior developer and
Yep.
then
Okay.
it would be for a data scientist career path. Where to start out as a
Yeah. So that's a good question. From what I've seen, it depends. If your organization is like, there's two options there, right? So organizations that are very new don't have well-defined processes or roles, and so you can sort of get to define what you're doing. If the organization is like expanding rapidly, defining itself all the time, right? So like there's a lot of freedom there, but also a lot of uncertainty, right, in your role. And so in contrast, if you're with an existing organization, like I am an organization that's very old, and so therefore has well-defined bureaucratic processes, and they have well-defined roles. Data scientist as a role is very new. So I'm in an organization which has like, if you're an engineer, there's been tons of engineers that have gone through that organization and they know exactly what to do with engineers, right? They know what to do with lawyers. Lawyers go through another track, right? Data scientist, it's a new position. So right now, my organization is sort of like flummoxed of like, what do we do with these people that we've never seen before, do a bunch of different things, and they don't have this like narrow definition, right? Because like intrinsically, a data scientist is crossing all these different domains, so we can't put them in a silo, right? And that's causing some problems because we don't know how to answer that question as an organization.
Yeah, I think that, a lot of the articles that describe the need that's not there.
Exactly.
It's like, well, are you a manager? Are you part of the bunch of data scientists?
Exactly.
You kind of just go by your amount of experience, and that's worrisome.
Yeah.
For some of it.
So I think, so what I've seen is that the people, so there were data scientists before that role as a title existed. And so those are the people who are sort of answering your question of like, what are they doing now, even though they are data scientists. So a few examples are, there are people who have remained the core technical data science role, even though they've just gotten older and gotten paid more. So staying technical is one option. Another option is like, because you have a bunch of different exposure to different problems, you become very attractive as a project manager because project managers are responsible for coordinating a bunch of different aspects on a project. So that's not quite a manager role of people. It's more like a project manager of different problems within a project. So data scientists sometimes fall into that. And then just because of what I do, I fall into the category of like organizational debugger, of like trying to figure out like, what are all the problems? What do we do about, where do we spend the most effort, right? And like talking to a bunch of people all the time, and like also little prototype demos of like, here's what we could do. So there's fewer of those people, but because again, you have the technical skill and the ability to communicate across domains, those are attractive skills for that type of role, which is less well defined.
I think it's just like, I started out as an analyst.
Okay.
It's always been like two types. You either become fully functional, you become a project manager at the end, or you stay technical and you become, at least from a developer,
architect.
Yep.
Or the main architect. It seems like it's the same path.
Similar, yeah. I guess you could call that last role the organization debugger and the architect.
Yeah.
But I guess
I think that's just like.
yeah, I associate architect with someone who has a responsibility for the architecture. Typically, people aren't given that easily. So,
Yeah, I think you're gonna have run into like less of that, like where do I do next? Really big organizations, basically. At a company like Google, there's gonna be like a million different things to do with data science.
yeah, you can, and along that line, you can also like hop into different roles pretty easily because you have a little bit of touch on each one of them. So, like if you do want to go deeper into theory or more into practice, or switch domains, like those are more like if you were only an electrical engineer and that's all you knew from your education and your experience, it's harder to hop roles into a different transition to a different role. Whereas a data scientist is more nimble in the roles that they can take on because they have more diversity. Yeah, you can definitely. I have resisted the push into management. I don't know what the consequence of that is, but that's a choice. Other questions on career comments? I do not consider that a rambling, a waste of my time or yours. So that was an intentional sort of diversion. All right. So earlier we talked about histograms. This is almost the last section, so we're on track for time. So I was talking about the number of choices of bins. Those are reflecting the ease of which your consumers can understand the information. There's also mistakes that people can make that either are intentional or because they don't know any better. And I would hopefully lump a lot of these under the didn't know any better, but it has a consequence on the way the story's edited. So this is an example of where I take some data and I want to emphasize the difference, and so I set the scale to be not equal to 0 down here, right, which is a purely common problem. Because when you actually plot it with a 0, you say, like, yes, there's change, but it's almost inconsequential, unless that somehow matters to you. Okay, and the point of me telling you all mistakes is so that you do not make them, unless you intend to. All right. So there's plenty of examples lying around the internet of people making significant mistakes with visualization outcomes. And so this is sort of like a warning that it really can happen, whether malicious or accidental, but in some sense it doesn't matter. Right, so did everybody see this? Like this is from a TV show, this is from a sports game, and this is from something that was published. So people really do make bad mistakes. All right, so I'll cover this in a little bit more depth in the time series class, but when I say average, you should ask which average. And this is hopefully a new question, because like I wasn't exposed to this until a few years ago. But it turns out which average, there's 3 different averages from. So what we're used to typically is arithmetic mean. That's like taking up a sum of all the different values and then dividing by the number of values you have. That is the arithmetic mean. There's different definitions and there's different motivations for why would you use the harmonic and geometric mean. And you have to sort of like, when you use these alternative methods, you should be very clear and explicit that I'm not using the normal sense of average. And it is valid to use some of these. So for instance, if we're looking at heart rate, the average heart rate, right? The sort of like naive expectation is it's an average, so I'll use the arithmetic. But since it's a rate, right, beats per minute, I'll have to use the harmonic. So this is another sort of like quick gotcha that people typically aren't even aware of. So the point of this slide is to say these things exist, know that there are cases when you should use them, and be explicit about the fact that you didn't use what people are expecting. All right, and then my last advertisement before we finish up is that I talked about a bunch of math that you probably are familiar with. There's a whole another domain of application that I probably won't talk as much about, which is A/B testing So you might have heard of this where a website presents their web page to you, and you're like, looks good, right? I'll just use it, blah, blah, blah. Some other customer going to that same domain, different website. And the intention for the business to do this is to figure out which one of those representations of the website is more likely to result in you buying their product. So you are part of an experiment the business is running to maximize their profit. And so they make a bunch of like really minor changes, right? So like, let's say you go to a web page and then the buy button is green, right? Someone else goes to that same web page and the buy button is red, right? If you look at a whole bunch of people going to that same website, right, which one of those page designs results in a higher probability of the people actually making the click on the button to buy the product? It's a relatively straightforward concept. So sort of like now that you know that it exists, you can apply it to every single element on the web page, right? And that would only be reasonable if you have hundreds of thousands of visitors to your website, which Amazon, Microsoft, Google, they all have lots of visitors, right? So they are constantly optimizing the way in which they render their pages to maximize whatever objectives they have. Right? So this all falls under this sort of like general heading of A/B testing. The reason it is present here in the math course section is because there are some statistics that you have to be aware of, right? So like if I say, I'm going to look for whether this feature improves the outcome that I'm interested in, and then you run it on 100 customers. Maybe that 100 customer sample size wasn't large enough to be statistically meaningful. And so you have to have some understanding of like, how long should I run the experiment for? How many people visiting my website make a statistically meaningful sample? And like, that sort of question gets really complicated when you're tuning all of the different parameters on your website at the same time. And again, this is only usually accessible if you have lots of visitors, because if you only have 3, good luck with an A/B test. Questions on that? So, oh yeah, I had an application for this. So you also get this in email. So like when a company sends you an email, they typically want you to click on something or read the content, right? Has anyone gotten an email like that? Yes, we're good. All right, so what? So I could send out, I have this email distribution list, right? The email distribution list has 1,000 people on it. And so I split my email distribution list into 2 lists. One we'll call group A and the other group B, right? And we'll send them almost the same email with either slightly different wording, slightly different picture, maybe a different link, a little teaser, right? Whatever slight modifications I want to make, and I send the original email and a slight modification to those 2 lists, and then I see which people in which group clicked on the thing that I wanted them to more often. Right? So you can do A/B testing with email, right? Or any other sort of like thing where you're sending out content to a bunch of people and you want them to take an action, you can measure their responsiveness. All right. Okay. Questions on that? So it's like a whole, this is a disclaimer of a thing I'm not covering, but you should be aware of because some of you may end up using this as your work rule, right? That's like a common data science sort of application. All right, statistics, yay. All right, I think that's it. All right, so we're gonna take a little bit of time to do a homework. Before I get that, Hector asked about an email that was sent out. There was an email saying like, don't cheat. And Hector's question was, what does that mean? Well, to restate what's in the syllabus, the intention there is that I have stated that it is okay to talk to other students about the design of your homework. That's acceptable, that's not cheating. If you share code with other students, that is crossing the line into plagiarism. So that's my boundary. Does that answer the question? So sharing code isn't naughty. Talking about design, perfectly acceptable. The danger is like if someone's design discussion turns into, well, what about this variable? And that's probably going to cause some issues. Does that answer? Okay. All right, homework time. So I've got 2 homeworks. There's going to be 2 notebooks required back for the solution set. So they're separate efforts. The first one is talking about that power source data that I looked at. So there's going to be creating 2 pictures from that data. And they're both about the power per hour, but they're slightly different pictures. One is you're going to have 24 bars because there's 24 hours in a day. And the other is going to have as many bars as you have days of data times 24. And then the other problem is a little bit more complicated to describe. I have two die. This is a die, right? So dice, die. Right. So I roll a die, and I get either a 1 or 2 or 3 or 5 or 6. 1, 2, 3, 4, 5, or 6. That's a fair die. Right? If I roll a die that maybe is like weighted, like has some little bit of weight in it, it's more likely that one of the outcomes will show up more often. And that's a weighted die or a biased die. Okay? And so I'm telling you that there is a die that has an unfair outcome. And so my question to you is, if you roll both of those die many times and you record the results, will you be able to distinguish what the outcome of those two die is? Okay. So I'm either getting a lot of blank stares or everybody's bored by this. So we're going to write down for whichever one of those problems you want, what it is you're going to do, and then how we're going to do it. And there'll be a reading from it. So again, this is the homework assignment. We have 7 minutes to figure out how are you going to solve those problems. And so why am I doing this in class? It's so that you can ask me questions in front of everyone so that we can all get the same consistent answer of the obvious things, right? So I try to write these somewhat clearly, but I understand that they're not well defined in the usual homework sense. Yeah.
Which is probably the answer. How are you finding ways to evaluate?
Yeah. So if you think back to the coin flip, sort of assumed that those outcomes would be fair, right? So we didn't bother assigning the outcome probability of heads versus the outcome probability of tails. So you will need to figure out how to assign an unequal distribution to a set of outcomes.
What's a suitable sample size of rolls and die?
That is a good question that you will have to answer by figuring that out. So the homework doesn't say like do 1,000 rolls of each die and that will tell you whether or not the dice is fair. But the goal is that you should be able to take any value that a user would provide as an argument to a function as your input. So did that clarify it? It's again, so it's just like the generating the random data where I don't have an answer. I want to be able to put in that number. And again, these are they're not simple probably, and so you do have spring break. Good news. Happy spring break. And I'll be available. I'm not wandering away.
So these aren't due next week, the following week?
There is no class as far as I know next week. So yes, that's correct. All right. Yeah, like I think the next class is the 27th, so these will be due on the 26th. I believe. Okay. Well, while you're stewing on that, there is a reading assignment. There is no essay associated with this reading assignment that I'll be grading, so it's just sort of like I highly recommend some reading. And then I think, yeah. Does anyone have any other questions on the homework before we bust out to the last little interaction? All right.
You want to sum the two die?
No, there's no need to sum the die. They're independent. They have a fair die.
You want to see the fair die?
I think you're asking how would you detect that they're not fair? Is that what you're asking?
I'm necessary.
Okay, so no sums, as far as I understand, would be necessary to solve this problem. All right. And then the last activity is to find a person that you haven't talked to recently. And I think if you default to the person who's next to you, that's like a too easy of an answer. So like,
What'd you do?
exactly. So you're going to talk to someone about what you learned in class. It's a real challenge. We've got 3 minutes. I know that you can do this in 3 minutes.